Alright, so now we're finally ready to start talking about the line integrals of vector fields. So far we have looked at line integrals of scalar fields, such as the one here. So f of x, y is a scalar function, and then we take respect to some element of arc length ds. So that is the line integral of a scalar field. Now, what if we have a vector field? Well, things get a little bit more complicated. And just to give you an idea of how this works, I'm just going to give you an example of why you would need to do an integral over a vector field. So suppose that you have a particle that is going from one point A to one point B, and then that particle is going to follow a path that is basically described by the curve C. Now, the displacement of the particle at any point, it can basically be traced in terms of an infinitesimal vector r, where r is just the vector of position. But if you wanted to be a little bit more general, you could basically just find a point of reference on the x, y, z axis, and then basically just trace a vector that goes from here and then just follows along that path, and basically that's going to be your vector r. But if you wanted to just have the infinitesimal r, basically that's just oriented along the curve C. Now imagine that you have a force field that is acting on that particle, and that force field could be anything. It could be a gravitational field, it could be an electromagnetic field, it could be just anything that is actually acting on that particle that is pushing it to go from point A to point B along that path C. So in that case, what you would do is you would notice, well, a vector field essentially has a bunch of different vectors and they're pointing in a specific direction. They all have different magnitudes. So depending upon which part of the vector field this curve is falling into, the force at each of those points is going to be different. So in the end, what you actually want to do is, if you want to just calculate the total magnitude of how much energy is being spent on moving that particle, given some force on that force field and some displacement, what you would do is the following. You would take the dot product of the vector field at some point. So let's say we take it at some point k, and you take the dot product with respect to with some change in displacement, rk. And now obviously the idea is that you're going to take this over an entire range here. So basically you're going to say, we're going to take the sum of this, and that's going to give us the total contribution along this path. So you're going to add up all those little contributions. And it turns out that this definition, if you take it to infinity, this is going to be the work. So the work done on a particle, if you remember from elementary physics, is just force times distance. So if you apply a force in a particular direction along some distance r, then the total energy that was spent performing that action is going to be given by the work, and the work is calculated in joules. So the work is just, if we take it to a more elementary level, we're going to have this. And obviously, you know, if you take, say you take a limit as this goes to an infinitesimally small value, as this approaches 0, then what you have is an integral. So you're going to have the integral of the vector field, dot product with the element dr, and then this is going to be the work. So basically you're going to take the sum of that dot product along the entire curve C, and that's going to give you the work done on that particle by that force field. So how does that actually work? Well, it turns out that if you parameterize your curve, so basically let's say that C is represented by some parametric curve R of some parameter t, then what you can do is you can say, well, dr over dt, because we know that you can differentiate a vector quantity, basically this is going to be equal to r of t, like that. And then basically dr is going to be r of t times dt. So now what you can do with this is that you can plug this back into the original equation, and you can say, well, the work done on that particle is going to be the following. We're going to have some curve C. We're going to have the vector field. Now we're going to represent it as a function of t. So basically we're going to make x, y, and z all functions of the parameter t. And you're going to take the dot product with respect to this element here. So that's going to be dot product with the first derivative of r first derivative of the vector, and then times dt. So this is essentially how you would find the work done on a particle based on the force field. So how does that actually work? Let's work through an example just to illustrate how this actually is used in physics. So let's say we're given some force field that is described like this. So it's just a force field in 2 dimensions. And we have a curve that is basically just a circular arc that goes that covers just the first quadrant on the xy plane. So basically we can define this arc. Our C is just going to be defined as follows. X is going to be cosine of t because the radius of this arc is 1. And then y is just going to be sine of t. So basically this just comes from polar coordinate parameterizations. We have cosine of t. So in this case the radius is 1, so we put 1 there, and then y equals to 1 sine of t. Alright, and now in order to evaluate the limits, so we know that the parameter t, which is in this case just the angle of rotation, it's going to go from 0 to pi on 2 because it is only covering 90 degrees or the first quadrant. So now what we're going to do is we're going to basically need to put this back into the force field. So the force field in terms of this parametrized curve is going to be the following. We have x squared. Well, x is just cosine of t, so this becomes cosine square of t. And then this right here is going to be minus sine of t cosine of t. So I just changed the order of multiplication. And this is going to be the new force field in terms of that parametrization. So now, in order to calculate this, what we need to do is we need to take the derivative. So basically, I'm going to write this as follows. dr is going to be equal to the force field dot product of r differentiated with respect to time times dt. So we're going to find out what this r prime of t is. So r prime of t is just the derivative of this vector. So if we differentiate this with respect to time, that becomes sine. Okay, if we differentiate this one, this becomes cosine. And now to find this quantity, so this is going to be here, f of rt dot product with this dt is going to be the following. We're going to have this quantity, cosine square of t, minus sine t times cosine of t, and then dot product with this vector, so that's going to be minus sine t, comma cosine of t, times dt. So dt is just acting like a scalar quantity multiplying everything here. And we know that the resultant of a dot product of two vectors is a scalar quantity. So this is going to become, we're going to have cosine squared t times this, so that becomes minus sine t cosine squared t. And then we're going to add this here, so basically this is going to be minus sine t cosine squared t dt, and we can regroup this, so basically these two terms are the same, so we have minus 2 times sine t cosine squared t times dt. So this is the integrand of our problem. So in order to find the work done on that particle by this force field, what we're going to do is we're going to write C of force field dot product with dr. And now we're going to introduce the limits of integration, so 0 to pi on 2. And this is essentially what we're going to have, minus 2 sine of t cosine squared t times dt. We can take out that minus 2, so that becomes minus 2, 0, pi on 2. And now we're going to have sine t cosine squared t dt. And now we can use integration by substitution, so basically make u equals to cosine of t such that the derivative becomes minus sine t times dt. So if we actually put that minus inside instead, let's put the minus inside. So let's just write this down. So we have cosine t, then du is equal to minus sine t times dt. Alright, so we already have our du here, and this is going to be u squared. So we have 2, 0 pi on 2 of u squared du, and then this is going to be 2 over 3 of u cubed. So u cubed is going to be cosine cubed t, and this is evaluated from 0 to pi on 2. And now let's see what we get. Well, if we draw our cosine function, we know that it goes like this. So basically at 0 we have 1, and then at pi on 2 we have 0. So basically we're gonna have 0 minus, we're gonna get cosine, so that's going to be minus 2 on 3. And then basically we're gonna have our work is just going to be minus 2 on 3 units. And the units would be energy, but we didn't give any units for the force or the position, so we're just gonna leave it at that. But this is essentially what that line integral of that vector field is going to be. And one of the interesting results from this is that you can prove this yourself. When you take the integral, so let's say you have something like this, this is going to be equal to minus the line integral taken from the curve in the opposite direction of this right here. So basically it doesn't really matter in which order you take. If you take the curve in this orientation or that orientation, as long as you can relate the result back to this by multiplying it by a -1, then you're going to get the right answer regardless of which orientation you choose to use in the first place. But this is essentially the physical application of line integrals of vector fields. There are a few other applications, but this is one of the most common ones, and I feel like this is something that is fairly straightforward to understand, because you understand that the force is just moving the particle along this path. So we're just taking a sum of all those tangential forces, which results from the projection of that force field onto the curve, which is obtained via a dot product.